Hello. So today we're going to talk about lens equations. And as we know, we have two types of lens. Basically, the convex, double convex lens, and we have the concave lens, double concave lens. And the convex lens or double convex lens, it's a converging lens. Converging lens. While the concave one, it is diverging lens. So basically, if you have a lens in general, let's say the convex lens, the curvature of this lens has a radius, or this curvature, for example, it has a radius of r. Okay, so this is r. Let's say this is r, capital. And the focal length, or each lens has a focal length, and this focal length, f, it's equal to r over 2. So basically, it's somewhere here. So let's have a normal type of an image in front of the lens itself. So if you have a center line for this length here, then basically, if we say that this is the focal length, which is half of the radius of this lens, basically, and we can say that the image location, this is going to be the image location, or the object. Actually, this is the object. And the distance of the object, let's say a distance of object. And basically for this one, we have the height of the object itself, height of the object. So having this object is going to create a specific image, okay? So to get the image for this kind of lens, basically, we need to do 3 steps. One of them, it's basically to go from the tip of this object and draw a line going to enter the center of the lens itself. So we call it this. And basically, the focal length, let's write the focal length on the other side as well. It's almost here. Approximately, focal length. Then we draw a parallel line to the center line. Then from here, from the middle of this lens, we go to the focal point. Somewhere here. So they have intersection. And also if we went from the tip of the object, and we went to the focal length at this side, and we're here, and we draw a parallel line to the center line, we should have all of them to intersect at this location, and basically this is going to be the image that we have created. So this is the image itself, which has a height of image, and it has a distance, this distance, which is a distance of the image itself. So in order to solve any problem of a lens, basically, we draw the object, we identify the center line that is going through the center of the lens, we identify the focal length location, then we put the image itself with the object and the location, or the distance of the object. Then we determine the height of the object. Then we have 3 lines, one going parallel to the center line, up to the middle of the lens, then going this way, passing through the focal length, and so on. Then we have one from here, from the tip ray, from the tip incident ray, going from the tip of the object, going to the center of the lens and on a straight line. Then we have a ray or an incident ray going from the tip of the object to the lens itself, passing through the focal length. Then from the lens, it went parallel to the center line. And basically all of these rays should intersect in the image location. And this is a real image that if you have a screen here, you can visualize the image itself. So for the lens equations, we have the 1 over the distance of the image plus 1 over the distance of the object. It's equal to 1 over the focal length. So this is the first equation. Then we have the second equation. It's about the magnification, which is equal to height of the image over the height of the object, which is equal to minus the distance of the image over the distance of the object. This is the magnification. So we see here that we had a magnification, as we can see visually, that the height of the image is bigger than the height of the object. Okay, and I'm assuming it is farther away from the lens itself. So this is the equation that we use in order to find all the numbers. And this, as we said, this is a real image. The situation is different if we have used the concave lens. Let's do something else. If we draw this object here at this location. So if you draw it at this location, we have this one from here. Then we have a parallel one. And go to the center, then the focal length. Then we can see from here, if we extended these lines, they should intersect in the new image, which is basically going to be a virtual image. So this is the setup for the converging and diverging lenses experiment. So we have first the ruler, we have the optics bench, we have the screen, viewing screen, a double convex lens with a focal length of 10 centimeters, double concave lens with a 15 centimeter focal length. We have the light source with a disc that could show different targets, like L4, the adapter, and basically the manual. So let's make the setup. First, I would like to select the 4 number, okay, as our target. And I would like to start to measure the height of this number, and basically the height of this number is approximately 2 centimeters. You can select the other target, which is the L1 or anything else, but I will use the 4 number. Then I will connect the power supply, turn it on basically, and put it on the optics bench. Then I will start with using the double convex lens. We place it, and we put our screen here. Then from here, we'd like to observe if there's anything happens on the viewing screen or not. So let's see, do we see anything? Yes, I see, but I maybe don't see this. So let's turn off the light. So here, I'm going to select any random distance between the light source and the viewing screen. And I'm going to move basically the lens itself either like far from the viewing screen or near to the viewing screen until we have a sharp image. Okay, so we can see there's some change here. So here, for example, we can see that it's an obvious magnification of the number 4, as we can see here. And we can measure the height of number 4. And we can observe also that the number 4 is flipped. Okay, so we can see here, number 4 here is pointing up, but number 4 here, it's opposite or flipped. So let's see, do we see anything else? We start to move. Okay, you can see also, we can see another number 4, but this is a smaller number 4. The height, it's obviously a small height of number 4 here. So basically, we are going to consider these two measurements, the one with the magnification and the one with kind of zoom out or like make it reduction of the height of the number 4. And we need to observe what's the difference between these two, okay, and why this is happening. So we have to measure the distance from the light source to the lens and from the lens to the image itself and observe. We can see that here the light source and between the lens, it's basically, obviously it is more than the focal length of 10. So we have a focal length of 10. So we are here approximately at 19. So this is 50, so it's approximately 30, which means it's the distance here is more than two times the focal length, while the distance here on the other side, it's basically more than one focal length, so it's between one focal length and two focal lengths, okay? However, if we approach this one in this direction and we get a focused image, we can see the distance here. It is more than one focal length, but less than 2 times focal length. But the distance here is basically more than 2 focal lengths. Okay? Something else you could do, you could, for example, change this distance between the screen, viewing screen, and the light source, and basically do the same. See what's happening. So nothing here, and start to approach. So it's focused, but it's not the best signal, so it seems to be here. The best signal is going to be here. And we take basically the distance from the source to the lens and from the lens to the image. And we comment on this. Now, let's replace the convex lens with a concave lens and see what is the difference. So this is a 15 centimeter concave lens. Okay? So let's observe. So if we did this, nothing happened actually. We don't see any image. If we make this one farther, you see it. Now we don't see it. Let's say here, and we keep going around. If nothing happened using the concave lens. But actually there's something interesting that I would like to show you to you. Let's look inside the focal lens, or like the concave lens itself, and see, do you see an image or not? So here, you can see inside the lens, basically we see the image through our eyes that there's a small number 4 inside. Hope you see it. It's an image of number 4. If we went closer to the light source, we see that the number 4 is getting bigger. If we went further from the light source, the number 4 itself, it gets smaller and smaller. You see this? It's very interesting. And you need to comment on this based on the equations and your understanding of the directions. Yeah, let's get it bigger. while getting closer to the light source itself. Okay, it's bigger, but still not as big as the original image. Let's go further. Anything is going to happen. It's just getting smaller. And we can see also that the image, it is not flipped. So nothing happened. I hope you liked the lab for today and you've learned something beneficial. If you liked it, please press the like button and subscribe, and wait for me for our next physics lab. Thank you.